The device you're watching this on right now, it is powered by literally flawless microscopic engineering. Welcome to this explainer. Today we're looking at something absolutely fascinating. When we think about chip manufacturing, we usually picture building things up, right? Depositing materials, etching lines, stacking layers, the whole shebang. But there's an entirely different, equally critical battle happening at the exact same time. It's the rigorous policing of completely invisible threats at every single stage. So we're going to explore the microscopic obstacle course of semiconductor inspection and detail exactly how manufacturers catch the tiny, hidden defects that can ruin entire wafers.
Okay, let's dive into this. We've got a very clear chronological roadmap for our explainer today. We'll start at the wafer prep checkpoints, move right into the incredibly delicate photolithography phase, examine deposition and metallization, test the individual chips during electrical die sorting, and finally wrap up with packaging quality control.
So, that brings us to a huge core question. How do you catch a multi-million-dollar mistake that you can't even see? I mean, in a multi-billion-dollar fabrication plant, the biggest threats aren't, obvious cracks or giant specks of dust. No, the real yield killers are completely invisible to the naked eye. A massive state-of-the-art facility can literally be brought to its knees by a tiny amount of stress in a crystal lattice, or just a slight drift in an exposure dose. Catching these? Well, that requires a serious arsenal of advanced inspection methods.
Let's start right at the beginning with our first major checkpoint. Number 1, the wafer prep checkpoints.
Before a wafer even begins its complex manufacturing journey, it has to be physically perfect. And optical thickness tools are heavily used here. They're fantastic at ensuring the wafer has a uniform thickness, and they check for bow, warp, surface particles, even microcracks. This is absolutely crucial for stable chucking, which is basically how the machine securely holds the wafer perfectly flat, and for lithography focus later on. But, and this is a recurring theme you'll notice in semiconductor inspection, one inspection method is never enough. Actually, optical tools completely miss the invisible yield killers, things like internal crystal defects, bulk impurities, and internal wafer stress.
Because those optical tools have blind spots, fabs deploy a whole suite of advanced metrology tools to inspect the surface treatment right down at the micro level. Think of these as highly specialized detectives. UV visible and fluorescent spectrometers, they check specific optical properties. XPS, or X-ray photoelectron spectrometry, actually bounces X-rays off the wafer to analyze its precise chemical makeup, kind of acting like a microscopic fingerprint scanner to spot contamination elements. TOF SIMS goes even deeper. It's like a chemical bloodhound, detecting even trace molecular residues, while ellipsometry measures the ultra-thin film thicknesses and optical constants of oxide layers. All these methods work together to ensure a flawlessly clean surface with the exact right electrical properties before that wafer moves forward.
Now let's see how this builds into our next critical phase. Number 2, photolithography and yield assurance. This is where the intricate patterns are actually drawn onto the wafer.
To really understand the inspection mindset here, I love this perspective from a 10-year veteran on-site process engineer. They pointed out that resist coat and bake uniformity are the hidden multipliers of every downstream step. Listen to this. A lithography engineer who only watches the scanner is missing half the problem. Yield loss from coating or baking non-uniformity is just incredibly insidious. It doesn't show up as some catastrophic visual defect. Instead, it hides in the tails of the measurement distribution. And honestly, it might only pop up way down the line at the electrical test. So engineers have to rigorously inspect these prep steps, not just the scanner itself.
So the crucial point is just how incredibly tight the margins are during the actual exposure. Take dose sensitivity, for example. That's the rate at which the critical dimension changes per 1% change in exposure dose. The exposure dose determines how much photoacid is generated. And in advanced nodes, a mere 1% change in exposure dose can shift the critical dimension of a gate by 1 to 3 nanometers across every single die. If a slight lamp degradation or just a tiny bit of lens contamination causes a 1% dose increase that goes undetected by your monitors, boom, you could instantly ruin a batch of 25 wafers, destroying every single potential chip on them in literally a fraction of a second.
And focus? Focus is just as unforgiving. Fabs implement strict flatness pre-screening before the scanner even gets to work. If a wafer has a local flatness error, known as SFQR, of greater than 30 nanometers, it is immediately rejected. Now, to put that into perspective, 30 nanometers is thousands of times thinner than a single human hair. The reason they're so strict is simple. Out-of-spec flatness that escapes into the scanner is completely unrecoverable, simply because the scanner cannot compensate for wafer bow beyond its dynamic focus range.
All right, once our patterns are perfect, we move to depositing layers and building the microscopic wiring. Let's look at Section 3, inspecting deposition and metallization.
Now that we're actually building the physical structures, the inspection tools have to adapt. Here, the obstacle course requires a massive, heavy-hitting arsenal of specialized gear to analyze complex materials. XRD, or X-ray diffraction, is out there hunting for lattice structures and invisible residual stress. Atomic force microscopy, or AFM, physically runs a microscopic probe over the surface to map the nanoterrain and surface roughness. XPS jumps back in to check surface composition and oxidation on barrier layers, and TOFS SIMS provides incredibly sensitive depth profiling to track impurities and trace dopants layer by layer.
Now, what's really interesting here is the ultimate goal, ensuring that after all that painstaking effort to perfect the front-end transistor implants, the back-end metal wiring doesn't suddenly become a new bottleneck. I mean, you don't want to completely negate the benefits of your optimized transistors. So we use tools like 4-point probes for sheet resistance mapping and scanning electron microscopy for high-resolution imaging of line-edge roughness. All of this ensures those microscopic contacts and interconnects are going to work flawlessly.
And this brilliantly illustrates the extreme danger of residual stress, which is another massive, completely invisible threat during deposition. Think about a material like titanium dioxide. It can exist in different lattice structures, like unattase, rutile, or brookite. If a process accidentally deposits rutile when unattase is actually required, an optical thickness tool will look at that layer and say, yep, it's absolutely perfect. But functionally, because of the mismatch between the deposited film's natural lattice parameter and the substrate, stress is secretly building up inside, and the device is functionally doomed to fail. You literally need X-ray diffraction working alongside surface profilometers to catch this invisible killer.
Eventually, all the physical processing finishes. And that brings us to our fourth checkpoint. Number 4, electrical die sorting tests, also known as EDS.
This is the moment of truth where every individual die on the wafer is finally tested to see if it actually, works. Modern EDS relies on automated test equipment, or ATE. These systems use specialized probe cards equipped with microscopic pins that physically make contact with the incredibly tiny bond pads on every single die. The ATE applies specific test signals, measures the die's actual responses, and then compares that performance right against the strict design specifications.
Think of this as a rigorous physical exam for the chip. To survive the EDS checkpoint, a die must pass a structured 3-step obstacle course. First up, DC parametric tests. These check its vital signs by measuring baseline electrical properties, things like supply current and leakage. Next, AC timing tests measure dynamic performance, basically checking its reflexes like clock frequencies and propagation delays. Finally, functional tests step in to verify that the chip actually does what it's supposed to do by running complex logic patterns and memory write/read cycles.
Now here is a pretty wild reality of semiconductor manufacturing. Not every chip survives this gauntlet. In fact, a typical wafer yield can range anywhere from 50 to 95%. Just imagine throwing away almost half your product just to guarantee quality. The AT sorts the results into different bins. Pass bins are for the flawless dies. Marginal bins are for those that are close to the limits. And hey, they might even be sorted by speed or leakage for premium pricing. And fail bins? Those are straight to scrap. The failed dies are physically marked with an ink dot or meticulously noted in the test data mapping, so there's absolutely no way they get used in the next step.
Those surviving chips move on to our final stage. Number 5, final packaging quality control. This is where the wafer is diced and the individual dies are mounted, interconnected, and finally sealed in their protective packaging. But even after the chip is sealed tight, the inspections do not stop. Manufacturers use a final, rapid-fire barrage of non-destructive evaluation, or NDE tools, just to cross the finish line safely. Automated optical inspection checks the outer surface quality and markings. Automated X-ray inspection looks for hidden voids or cracks in the internal connections, literally just like getting an X-ray at the doctor's office. Scanning acoustic microscopy uses high-frequency sound waves to hunt for internal defects and delamination, while thermal and IR imaging locate any sneaky electrical defects by looking at heat signatures.
All of which leaves us with this final, kind of provocative thought. If your main goal is maximizing long-term reliability for an advanced, high-density 3D package, rather than just getting a high initial yield today, how do you actually prioritize all these inspections? Catching a flaw early definitely prevents wasted money, but catching a subtle reliability issue at the packaging stage prevents a catastrophic failure in a consumer's hands tomorrow, meaning your car's safety system doesn't fail on the highway and your phone doesn't just randomly brick.
It's an absolutely fascinating balancing act in the microscopic obstacle course of chip manufacturing. Thanks for exploring this with me.